Begin with an overview of the contents of Chapter 3, Statistical Mechanics and Chemical Kinetics. We're going to talk first of all about the idea behind thermodynamic quantities and entropy in particular, then introduce the single most important idea of this chapter, which is the Boltzmann distribution, which tells you how the states of a system are occupied when the system is in thermal equilibrium with its surroundings. I then want to introduce the very useful idea of equipartition of energy, then turn to a definition of the partition function, which is the quantity used to derive thermodynamic quantities from microscopic models of a system. Then we will have a discussion of free energies and different definitions of free energies for different types of system, and then introduce quantum mechanical distributions and, very importantly, the Fermi-Dirac distribution. We then turn to fluctuations and show how the fluctuations in a system can be derived from the partition function, and go on to describe Brownian motion and diffusion, and then end with a discussion of chemical reactions. In particular, talk about the Kramer's model for reactions, our first example of an emergent phenomenon, and finish with a discussion of chemical kinetics. So, statistical mechanics is the program of deriving macroscopic quantities from a microscopic model. For example, in panel A here, temperature is illustrated as the kinetic energy of molecules. The higher the kinetic energy of these molecules, the larger the temperature. And this leads then naturally to the idea of pressure. If these self-same molecules are contained in a box, they will collide with the sides of the box, and because the collisions occur on this side but not on the outside of the box, there's a net force outwards on the box. This is the quantity that we call pressure. Illustrated here is the idea of work, which thermodynamically we think of as a force moved through a certain distance, but we're showing here that as one does work on this box, one increases the density of energetic atoms inside this chamber, and thus the internal energy of the chamber. We say the pressure has been increased by doing work on the box. Here's a somewhat more subtle illustration of a thermodynamic calculation, which is phase equilibria. One talks in thermodynamics of having the free energy in the two phases being equal when, for example, a gas phase is in contact with a solid phase. At the microscopic level, we think of the competition between the interaction energy between the atoms that holds them in the solid phase and the greatly increased availability of states in the gas phase, and the competition between this increased availability of states where the atoms are going to the gas phase and the binding energy holding the atom in place in the solid phase. Now that eventually leads to an equilibrium between the two phases. Chemical energy is illustrated on this next panel, where we show atoms combining. For example, we could have hydrogen molecules and oxygen molecules, and they come together to form water, and when they do so, a great deal of energy is liberated, and this results in an increase in the kinetic energy of the whole assembly. So chemical energy, a very important concept in thermodynamics. And finally, I show you something that's not an equilibrium quantity, but important in determining how a system comes into equilibrium, which is the idea of viscosity and friction. So in the macroscopic world, we would think of molasses as, say, slowing down the motion of a ball bearing that had been moved inside a can of molasses. At a microscopic level, we recognize energy is conserved and being transferred from the ball bearing to the molecules of molasses, which increase their kinetic energy, and therefore the work lost, or the energy lost by the ball bearing, is gained in heat by the molasses. All right. So now let's turn to a quick review of equilibrium thermodynamic quantities like temperature and pressure. We don't normally think of fluctuations in these quantities because we usually consider very large numbers of atoms. And so in macroscopic systems, quantities like temperature, pressure, internal energy can be defined to arbitrary precision. So let's take the example of the first law of thermodynamics. the change in internal energy of a system is just the sum of the heat flow into the system and the work done on it. The convention always is that if the internal energy increases, then we say delta E is greater than 0. So turning to this example here, let's just go straight to the exercise at the bottom. If a system absorbs 140 joules of heat from the surroundings, this increases its internal energy. So we say that the change in energy is plus 140 joules and does 85 joules of work on the surrounding. So the delta W then is negative. So this then will be the expression for delta E. Now, delta E is a state function, by which I mean that it is a well-defined quantity of the system. For example, if I do 1 joule of work to raise a weight above the floor, then its new state, increased in energy by 1 joule, is well-defined no matter how I got that weight off the floor. On the other hand, heat flow, delta Q, and work, delta W, are not state functions, because a given change in delta E can be achieved by many different combinations of heat flow and work. So let's take the example of a battery. If I connect it to a resistor, then the change in energy of the battery is just a loss of heat to the resistor. If, on the other hand, I take the battery and I connect it to an electric motor, say driving a little fan, then I lose heat both through the resistance of the windings of the motor and in the doing work to turn the blades of the fan. So I could lose this energy in many different combinations of Q and W. Viscosity is a very important concept. In Appendix D, we discussed the damped harmonic oscillator, and if you're not familiar with this, I would urge you to take a look at that appendix. But there, the idea of viscosity is used to show how if we put energy into 1 degree of freedom of a weight oscillating on a spring, it will be dissipated. This shows the oscillations damping down as a function of time as you pass energy to the molecules of the viscous medium. Now, when we talk about a system being in equilibrium, what we mean is that all the degrees of freedom have shared energy and are in effect at the same temperature. So getting to equilibrium is a very important concept in statistical mechanics, and most of the results we will derive are for the equilibrium case. So let me end then by discussing one of the perhaps more abstract ideas, but central ideas of how systems approach equilibrium. And this is entropy. So here I'm showing you a surface of potential energy against some coordinate. This could be, for example, ball bearings sitting in a wooden bowl with a dip in the middle and then a ridge and then a ring around the outside. And I put all of the ball bearings in this side and I start to shake the bowl. Now this state is the state of lowest energy, so if potential energy was the only consideration, then all of the ball bearings would eventually end up on side B here. But that's not what happens. Because I'm shaking the bowl, ball bearings will sometimes make a transition from B to A, so the actual equilibrium at the equivalent of a finite temperature simulated by shaking the bowl is a few more molecules or ball bearings in state B than in state A. This idea that at finite temperature the distribution is determined by another quantity in addition to the absolute energy difference between states, i.e. the temperature, is called entropy. So here's an example in which the potential energy of the two sides of the system, so it's a pair of compartments, all the molecules are on this side, we remove this compartment, we know that even although the potential energy of the particles is the same in box A as in box B, the most probable state is with an equal number of particles in box A and box B, and the driving force for particles to move from A to distribute equally throughout the system is called entropy.